Hello and welcome to the MOOC on optical communications. In this module, we will first complete what we have started in the previous module, that is discuss the power spectral density of polar and unipolar formats, both NRZ as well as RZ, and then consider the performance of on-off keying digital communication system, the digital optical communication system under the influence of fiber loss and other noise processes. Okay. So, let us begin by recalling the power spectral density, which we had denoted here as PSD, which was a function of the frequency f, and we had derived this formula for the case of polar format, right. For the polar format, we had derived this formula which said that you take the basic pulse shape p of t, take the Fourier transform of that, take the magnitude square divided by the bit duration Tb. Okay. If we assume, of course, now the power spectral density of course depends on the kind of pulse shape that we use. The simplest one is called as the rectangular pulse shape. Okay. The rectangular pulse shape, which is in our notation denoted as rect t by t or Tb, let us say, is actually a pulse of duration Tb, okay, and it is centered here at Tb by 2 minus Tb by 2, okay, and an amplitude of 1. So, this is your rectangular function which has a duration of Tb. If you are not happy with this pulse starting at minus Tb by 2, you can always make the pulse start at t equal to 0 and then have this pulse at Tb. Okay. Mathematically, there is a delay of Tb by 2 here compared to this waveform, and that will translate into a phase factor, but since you are taking the magnitude square, that phase factor will anyway go out. Okay. So, I will leave this as an exercise to show that the PST that you obtain for this pulse would be the same as the PST that you would obtain for this pulse. Okay. The shape of the pulse, with the amplitudes being the same, the shape of the pulse here has to be the primary concern, not its location. Okay. So, this is what we are going to consider for a rectangular pulse, right. So, we are to remind ourselves, we are looking at polar form and then we are looking at a NRZ format, right, because this is pulse which is occupying the entire bit duration. How would we represent a polar RZ duration? So, let us say this is still minus Tb by 2 and Tb by 2, but if I consider a rectangular pulse which is only half duration here, okay, I am considering a pulse whose duration is only half of the bit period, then this end will be at minus Tb by 4 and this would be plus Tb by 4, and this rectangular function can be written as rectangular function with a width which is only half. Okay. So, this would be the rectangular function. So, in fact, you can have a general way of representing this and then say rectangular function divided by x into Tb, where x will be a number that would be between 0 to 1. Of course, you can't really have it as 0, then it becomes an impulse and that is not what we are looking at. Okay. For a 50% duty cycle, x will be equal to 0.5. Okay. So, this corresponds to polar RZ format. Remember, in the polar format, one symbol is represented by plus 1 and symbol 0 is represented by minus 1. Okay. So, let us evaluate the PSD for both these cases. So, let us first start with the polar NRZ format. To call that one, let us call this as NRZ and also write this as polar format. Okay. This is some notation that I am inventing here because I have to indicate both the cases of NRZ, the format, RZ and the format. Okay. It is not a standard notation, it is just something that will distinguish the PSD for NRZ polar format versus RZ polar format. So, this one as a function of the frequency f, taking the Fourier transform of the basic pulse shape. Now, since the basic pulse shape here for the NRZ format is rectangular pulse occupying the entire duration, the Fourier transform of this, right. So, P of f will be given by Tb sinc ftb, where sinc function, as we will very shortly see, is defined as sin x pi x divided by pi x. Okay. So, this is what we call as sinc of x. So, if you substitute this expression P of f, then the magnitude of P of f square here will give you Tb square and sinc square. There is a Tb in the denominator here which cancels with one of the Tb in the numerator. So, what you get as the power spectral density is Tb sinc square f Tb. Okay. Let us also look at what you would get for the PSD of a polar format but RZ. Okay. So, you get polar format of the RZ here, since the rectangular function has a duration of TB by 2 or in general has a duration of x into TB, the corresponding Fourier transform here will be x TB sinc fx TB. Okay. And then when you square it, so obviously this will be TB square, but there is a TB in the denominator for the power spectral density. So, this will become x square TB, okay, and then you have sinc square fx TB. Let us sketch this as a function of the frequency f. Okay. You can also normalize this frequency by dividing it by TB, so you can do that one, otherwise you can just leave it as a function of f. So, for the PSD polar format, you see that this is a sinc square FTB function, and that function goes something like this. Okay. So, that function goes like this, and there are of course an infinite number of side lobes, but these side lobe amplitudes keep on dropping out. So, what would be the value of this sinc square at f equal to 0? That would be equal to TB, whatever the amplitude of the sinc square function at f equal to 0 will be TB here, and the first 0 occurs at 1 by TB, the second 0 occurs at 2 by TB, third one occurs at 3 by TB, and so on the positive frequency side. Similarly, on the negative frequency side it would be minus 1 by TB, minus 2 by TB, and so on. Okay. There are this infinite number of side lobes, which as you can see are carrying less and less energy or less and less power as you go higher and higher in terms of the frequency. So, if you were to arbitrarily define the bandwidth of this sinc square function as the frequency difference wherein the sinc square goes to the first 0, that is to say there is this main lobe, and if you define the bandwidth of this pulse as a main lobe pulse bandwidth, then the baseband bandwidth, because it only utilizes the positive frequencies, will be given by 1 by TB. However, when this pulse goes to the pass band, that is it gets modulated onto a carrier, then this instead of 0 you will have Fs, that is the signal frequency or the modulation frequency. Around that the main lobe width is 2 times or 2 by TB. Okay. So, that is the bandwidth of a NRZ format. Let us look at the RZ format bandwidth, and for this case we will assume that x is equal to 0.5. Okay. So, with x equal to 0.5, the amplitude of this function becomes 0.5 square, which is about 0.25 times TB, right. So, the amplitude at f equal to 0 will be 0.25 TB, which is fine, but where does the first 0 occur? The first 0 occurs at 1 by x TB, right. So, 1 by x is 0.5, so 1 by 0.5 TB, which is nothing but 2 by TB, and then the next 0 occurs at 4 by TB, and so on. So, the main lobe actually extends up to this point and then goes to 0 here and then goes to 0 here. So, it goes to 0 here and then goes to 0 here. Okay. It did not come out very nice sinc function because the amplitude has been scaled down and the lobe width has been increased. Okay. But if you are looking at the main lobe width, that main lobe width will be, so from the positive frequency side the main lobe width is 2 by TB, okay, whereas for the case of RZ it was just 1 by TB. Okay. So, for the RZ it is 1 by TB, for NRZ it is 2 by TB. So, with a RZ you see that there is a larger bandwidth requirement compared to the NRZ format. So, which means that why are we even wondering about whether use NRZ or RZ? If our goal is to reduce the bandwidth, then NRZ is preferred over RZ. However, with NRZ it turns out that the pulse is on all the time. So, whenever there is a 1, there is a 1, there is a pulse, only when there is a 0 there is no pulse. If you get a long string of 1s, what happens is that the DC value, the time average DC value over say last n block of pulses starts to become non-zero, okay, non-zero, and it will start to deviate from half. So, this process when it starts to happening, this is called as then this leads to a problem in the sense that your synchronization circuits do not really work very well. Okay. So, in order to avoid that, one utilizes not an NRZ format, but with a RZ format, which more or less tries to keep the average value around 0. Okay. For a polar format, the average will be around 0. For a unipolar format, NRZ is even worse, because the average is as such something like half, and then you start having non-zero, the average starts to deviate from 0. Okay. This phenomenon is called as baseline wander. Okay. The baseline that you are going to use for the threshold starts to wander, and this happens when you get a sequence of long ones. With RZ, there is a transition going on, so you can just pin down where the zeros are. So it helps in synchronization is the short answer for that, and we can use NRZ or the RZ depending on whether that synchronization problem is severe or not severe. In optics, we sometimes use NRZ format, or we use NRZ format, we do not really use RZ format because of additional problems. NRZ format is slightly less prone to nonlinear effects than RZ format. We will come to that one when we discuss fiber based fiber based nonlinearities and how they would affect the performance of the system. Okay, let us look at one more format, which is the unipolar format. In the unipolar NRZ, I am not going to derive the power spectral density in this particular case. Remember, for the unipolar format, symbol 1 is a pulse or a +1 amplitude, and symbol 0 is 0. You are not sending anything over here, and the polarity of this pulse is always single. That is why it is a unipolar format. The power spectral density of the unipolar format and NRZ turns out to be TB by 4 sinc square FTB, okay, and 1 plus delta F by TB. Do not be thrown off by this delta F term. This delta F is just a delta function which is present at F equal to 0. This part which you have seen is exactly similar to the RZ format, except that the amplitude has reduced to TB by 4, right. Rather than having an amplitude of TB, the amplitude has reduced to TB by 4, plus there is a delta function at the origin. So, if you were to sketch that, you would see the sketch to go something like this. So, this is F and you are looking at the PSDs. So, you have an amplitude of TB by 4. So, let us put that one, which goes to 0 at 1 by TB, and then similarly a symmetric one at -1 by TB, and so on. In addition to this, there is a delta function. The amplitude of the delta function is given by 1 by TB. Okay. So, this is a delta function that exists for the unipolar NRZ format. For the unipolar RZ format with a 50% duty cycle, you do get this behavior. In addition to this, okay, the amplitude of course is smaller because there is a factor of x sitting there for the RZ. So, the amplitude may be something that is smaller here. The width of course is larger, right. So, you have a width of say 2 TB. Okay. So, you have a width of 2 TB, and interestingly you also get a sequence of impulse functions. So, you get one impulse here, you get one impulse here, or rather you get one impulse here, you get one impulse here, and then you get one more impulse here, here, and so on. So, you get one impulse every 1 by TB, and then you get a something at 3 by TB, not here. So, not exactly over here. So, you get an impulse at, this is 1 by 2b, this is 2 by TB, this is 3 T by T. So, this is where you get one more impulse, okay, here. So, you get these additional impulses, but those impulses can actually be now used for carrier synchronization. So, in case you are looking at why this format is interesting, is because you have a series of impulses which you can pick off for carrier synchronization. So, we will stop with this pulse formatting and look at the next topic, which is going to be about performance of on-off keying systems, which is subjected to only fiber loss and noise processes that typically occur in a photodetector circuit. Okay. So, on-off keying system performance is what we are interested. In the next module, we are going to look at the performance in terms of, the next module we are going to look at the system performance because of dispersion. For now, the focus is to look at losses. How would losses impact the performance of on-off keying systems? Okay. Let us first review what on-off keying system is. Whenever you want to transmit a symbol 1, you can do so by transmitting an optical pulse. Okay. The optical pulse has a certain peak power P1, let us say, the duration is of course Tb, right. When you want to send a symbol 0, you do not transmit anything over the duration Tb, you do not transmit anything. If for a general case, if you want, you can also transmit a slightly different power. Okay. So, you can transmit a power which is say P0, P0 is greater than 0, but normally you do not transmit anything for a symbol 0. Okay. The transmitter side system consists of laser which is producing your continuous waveform. So, you have a laser here which is having a carrier frequency of omega s. This can be pulse shaped using one of the pulse shaping components that we discussed, such as a Mach Zehnder modulator, and then you have a amplitude modulator that you can use, okay, in order to turn on and turn off the pulse shaping circuit. Okay. In fact, if you are not really concerned about the exact pulse shape, then you can eliminate all these components and simply use a Mach Zehnder modulator in order to generate both pulse shape, because you are naturally getting a pulse shape as well as, and then you bias the Mach Zehnder modulator with the data at such that the Mach Zehnder modulator appears to give you 0. So, you can do both pulse shaping as well as on off keying modulation in the same device. Okay. So, you can do the same device and then transmit it over the fiber. Okay. So, in addition to this channel, there might be additional channels that are propagating, but that is not of interest to us. Okay. There might be additional channels, there might be something else coming off from the optical fiber network. We are not really concerned about that. What we are concerned about is, if you imagine that two parties are there with transmitter and receiver in a single span, that is, there are no repeaters in between, you just have an optical fiber connected between transmitter and the receiver. So, at the receiver what you will have is a photodetector. Okay. The photodetector circuit is very simple. You just have to have a photodetector followed by either a load resistor in order to convert the current into voltage, or you can have a transimpedance amplifier which will convert this current into voltage, but in a very nice manner, in the sense that it will not load the circuit. Okay. So, you have a photodetector followed by a threshold device. Okay. The objective of the threshold device is to simply look at the photocurrent that is received. If the photocurrent is above a certain threshold, then it will declare that as a bit 1, and if it is below threshold, it will declare as a bit 0, right. That is what you would expect. When you transmit a symbol 1, you expect the optical power to be greater than 0 and it must be greater than a certain value, right. So, you can define that as a bit 1. If the power or if the photocurrent is less than the threshold, so this is a threshold, so if the threshold it is less than the threshold, then you simply declare it as the bit 0. Okay. What can go wrong here in this circuit? What can go wrong? There are two things that are going wrong here. Fiber does not preserve the same optical power. For example, at the output of the Mach Zehnder modulator, if the optical power is P1, it will not be exactly the same power that you get when you receive it because of the fiber losses. So, there will be losses that are induced by the fiber which reduces the optical power. Okay. If the optical power reduces very much because the length of the fiber is very long, okay, if you use a long length fiber and the optical power is very small, then there is nothing to detect and then you will not really be able to distinguish 1 and a 0. Okay. You do not want to get into such a situation, but you want a sufficient length of the fiber and a minimum optical power. So, you want to operate at the largest optical link while maintaining the minimum optical power that is possible. Okay. There is a trade off here. If you go slightly beyond this way, then the power that you are going to obtain will be very small. On the other hand, if you come here, this might be just the critical value of the optical power that is received, which can be still utilized for detecting and differentiating between bit 1 and bit 0. Okay. So, that is where we are looking at. So, that is one of the things that can go wrong. The second thing that can go wrong is in this circuit, the photodetector and the optical receiver circuit, you find noises, right. What kind of noises do you find? Well, we have already seen the short noise, which is what would operate in a circuit such as a transimpedance amplifier, and when the optical power is sufficiently large. So, you have a optical power sufficiently large enough such that the short noise can dominate over the thermal noise, and that is where you would like to behave. Okay. I mean, you would like to operate the system. So, short noises dominating thermal noises when the optical bit corresponds to symbol 1 is a typical condition. However, when the bit is 0, you are not transmitting any optical power. So, the short noise has nothing to, there is no input. So, unless there is a mean photocurrent, short noise does not enter into picture. So, there is no short noise when you transmit 0 symbol. The noise in a transimpedance amplifier is kind of very difficult to evaluate at this, for this course level. So, we will assume that the thermal noise is coming mainly from the resistor that you are going to put. The load resistor RL is the one that is giving you thermal noise. So, these are at this point the only things that are going wrong in our model, and we want to evaluate what happens to the signal. Okay. So, let us try doing that by first looking at what we are going to receive and how we are going to operate this threshold device. Let us also look at a little bit more on the losses as well as the noises. Okay. What would the losses do? Suppose you transmit power P1 when you are transmitting a bit 1 or the symbol 1, when you are transmitting that bit, you start with a power P1. However, as a function of the length of the optical fiber, this power P1 starts to drop. So, at some length L here, you say that okay, I am going to stop at this point, okay, because if I let it go further, then the optical power would be reduced below what my detectors can receive or detect, right. There is something called as detectivity and sensitivity that we talked about. There was this concept of noise equivalent power, right. So, your signal better be at least couple of noise equivalent powers high, so that you are able to distinguish that optical power from the background noise. Okay. So, you want to operate your detectors with a minimum detectable level, but you can't really operate it below the minimum detectable level. Okay. So, you do that one. So, at this point the received optical power, we can write this as P1R, will be given by 10 to the power minus alpha into L times P1, where this 10 to the power minus alpha L I have used because this alpha is measured in dB per kilometer, okay, and L of course is the fiber length. So, if for example the losses are 0.2 dB per kilometer, then if I go a length of 80 kilometer, then the total losses that I am going to look at will be 0.2 into 80, which is 16 dB. Okay. And if I start my optical power at 0 dBm, which is already pretty high, 0 dBm corresponds to 1 milliwatt actually. So, this power which I am receiving will be minus 16 dBm. Okay. So, this is what I am actually receiving. So, anyway, the point here is that you get this P1R. Now, this optical power that comes in must go to a photodetector. Now, what would be the output of the photodetector? It is a photocurrent. The photocurrent that you are going to get with a bit 1 will be the responsivity of the photodiode times whatever the optical power that we have received, which is R into P1R. Our life would have been so simple if this is what we received. Unfortunately, what we receive is not just this mean photocurrent or the average photocurrent, but also the short noise, right. And what about the short noise? Well, we know the short noise variance. So, let us call this as sigma 1 square, indicating that this is short noise when bit 1 is transmitted. This short noise depends on the mean photocurrent level. The larger the mean photocurrent or the larger the optical power, you get a larger short noise variance. So, sigma 1 square is given by 2q, the mean value of the photocurrent, which I am denoting by these brackets, times. So, if you have an optical bandwidth, sorry, if you have an electrical bandwidth of B, then the total noise in that bandwidth will be multiplied to the spectral density. So, this is the power spectral density that you are looking at, and then this is the bandwidth that you are looking at. Okay. So, you assume that optical bandwidths are the filters that you are going to put are pretty large in bandwidth. Okay. So, normally before you even put this through the photodetector, you put a optical band pass filter. Okay. This optical band pass filter bandwidth should be sufficiently large compared to the electrical bandwidth, and we have assumed that condition. After the photodetector amplifier, you normally put a electrical bandwidth BE, or in fact it is kind of integrated along with the photodetector circuit itself in order to see what is the overall bandwidth. And I am not distinguishing between optical and electrical because I am assuming that optical bandwidth is very large. So, I am only concerned with the electrical bandwidth, and I just written that one as B here. Okay. So, this is the short noise. There will be thermal noise as well. Okay. So, when you have sigma 1, there will be thermal noise. Assuming that this is a load across the load resistor, what would be the thermal noise component? It is 4 kT divided by RL into B. right. This is the current noise variance that we are looking at. So, the spectral density is completely independent of what the received optical power is. The case with symbol 0 is very simple. With 0s you are not transmitting any optical power. So, no optical power here. So, therefore, there is nothing that is being received. So, you do not get sigma 0 square, right, sigma 0 short noise. So, let us write this as sigma 1 short noise, and sigma 0 short noise square is equal to 0 because there is no optical power, and we have assumed that all the background light is all gone. Okay. So, what you get is only the thermal noise, and thermal noise is independent of what you are actually seeing in terms of the optical power, and anyway in this case there is no optical power. So, this is the thermal noise. Clearly the total noise variance, right, which we can call as sigma 1 square, will be the sum of short noise variance and the thermal noise variance. Because these two processes are happening independently of each other, we can combine the total variance, we can obtain the total variance by adding these two together. Okay. And sigma 0 square here is simply sigma 0 thermal noise square, and one of the most important things that happen with an optical communication system, a digital optical communication system, is that sigma 0 square is less than sigma 1 square. Okay. If you assume these two are Gaussian random processes, a typical Gaussian random variable, the probability density of that is in the form of a Gaussian having a mean 0 and a variance of sigma. Okay. We normally indicate that by writing this as n of 0 comma sigma to indicate that the variance here is sigma and the mean is 0. And in an electrical communication system, this variance would be the same whether you transmit bit 1 or bit 0, because short noise is not there, unless we are of course using devices which have short noise. We will assume that we are not doing that. Because of the short noise that is present, sigma 1 square depends on what is the optical power that is being received. In other words, what is the photocurrent that determines the variance of the short noise, which in turn determines the variance of bit 1. So, when you transmit bit 1, you are not transmitting anything on bit 0, okay. You are transmitting only optical power on bit 1, which causes, this is the current axis, okay. So, this is the I axis or the current axis. The mean photocurrent that you are going to obtain when you transmit bit 1 is non-zero value here, and it is given here, and there is a certain variance of the noise process. This variance of the noise process is because of both sigma thermal noise square and short noise as well. So, this is sigma 1 square, that is the variance of this is concerned with sigma 1 square. What about 0? Well, for 0 the mean photocurrent is 0 because there is nothing that we are receiving, but there is a variance of the noise process here, okay, which is dependent on the thermal noise alone, sigma 0 square, which is less than sigma 1 square. Okay. It might not look very obvious, but the noise variance here is much more wider, the black one is much more wider compared to the green one. Okay. Green one represents the current mean, this is the mean photocurrent. So, mean photocurrent IPH of 0 is actually equal to 0. Now, what is this thresholding business that we were talking about? When you supposedly receive this current, okay, please note that this is the increasing current axis. When you receive this current here, you can then go back and then look at what is the probability of this current value, okay. This is the received current. This received current IR, there is a certain probability of this to come from bit 1, and there is a certain probability that it must have been just a noise coming from IPH 0, that is to say coming from bit 0 transmission. Okay. If you want to distinguish which one it is which and to minimize the errors in that decision, you normally choose a certain threshold point. The way to choose a threshold point here would be to choose the current as the point where these two probability density curves meet. Okay. Any current value that falls in this region will be attributed to bit 1, any current that falls in this region will be attributed to bit 0. And when you send a 1, you might mistakenly classify it as a 0 if the value falls below this threshold, which we can call it as I threshold. If it falls below I threshold, then you might mistakenly consider this as a 0. If you transmit a 0 and because of the thermal noise the value of the current pushes above the threshold, then you might mistakenly assign a 1 to 0. When you do that, we say that you are committing bit errors, okay, and we quantify this by saying how many bit errors are you making per second, okay. So, this is the number of bits that are there in error per second, okay. So, number of bit errors per second, okay. So, this is what the BER is, and we quantify the system by this BER measure, and you want this BER to be very small, okay. Of course, very small would mean 0, but unfortunately that is not the condition. Typical values of BER in the optical communication system at say up to 10 Gbps was around 10 to the power minus 9, okay. These systems did not have any coding or anything, so this was around 10 to the power minus 9. 10 to the power minus 6 was kind of acceptable, but 10 to the power minus 9 was preferred. What is the meaning of 10 to the power minus 9? It means that you transmit 10 to the power 9 bits, but 1 bit will be in error. If the bit rate is 10 Gbps, which means that you are transmitting 10 into 10 to the power 9 bits per second, and my probability of bit error is 10 to the power minus 9, then how many bits are there in error per second? Well, 10 into 10 to the power 9 bits per second, and probability of bit error is 10 to the power minus 9, okay. So, when you multiply this cancels out with this, so you are going to get 10 bits per second. So, that is the bit error rate. This is bit error probability, okay. But the colloquial use is that you use the same value for bit error rate, you do not really talk about bit error probability, because you kind of normalize it with the transmission rate or the data rate. So, this is BER. In optical communication systems, you also find another performance measure which is called as the Q factor, okay. Q factor is defined as IPH1, which is the mean photocurrent that you are going to receive when you transmit bit 1, to the mean photocurrent that you obtain when you transmit bit 0, divided by sigma 1 minus sigma 0, okay. So, sigma 1 corresponds of course to the variance of the noise process when you have transmitted bit 1, whereas sigma 0 is the variance that you obtain after you have transmitted bit 0, okay. So, you can define this Q factor, and the relationship between Q and BER is roughly that Q square exponential of minus Q square by 2 is approximately the BER of the system. This is sigma 1 plus sigma 0, okay. So, this is not sigma 1 minus sigma 0, this is sigma 1 plus sigma 0. Remember, in electrical communication system, sigma 1 is equal to sigma 0, okay. Therefore, they normally talk of either the signal power to the noise variance. Noise variance is usually defined as N0 or N0 by 2 depending on one sided or two sided power spectral density. So, there is no specific difference between the noise processes for sigma 1, or that is for bit 1 and bit 0. Here you have to distinguish between the two, and clearly the Q factor for the on off keying system will have only the mean photocurrent for bit 1, because mean photocurrent for bit 0 is 0 divided by sigma 1 plus sigma 0, okay. So, this is what the on off keying Q factor would look like, and the relationship between the BER and this fellow is roughly that exponential of minus Q square by 2 divided by square root of 2 pi into Q into square root 2 pi is bit error rate, okay. So, you can convert from the Q factor to BER. If someone gives you the Q factor, you can convert that into corresponding value of BER, and for a BER of 10 to the power minus 9, which was quite common in 10 Gbps optical communication systems, the corresponding Q value is about 6 dB, okay. And if Q is greater than 6 dB, well, the BER is actually less than that, okay. So, that is the point, and if Q is small, the BER of course becomes large, okay. So, this is all about the performance of the system, and as you can clearly see, the performance is determined more or less by the loss. Why is it determined by the loss? Well, what is the photocurrent that you have received? The photocurrent that you receive is R times P1R. P1R itself is given by P1 10 to the power minus alpha L by 10. When you express alpha in terms of dB per kilometer, you might want to write down 10 to the power minus alpha L by 10. If you want to express this one in the natural units of Nepper per meter, then this would be e to the power minus alpha L, Okay. So, let us say whatever that is, this is the received optical power multiplied by R will give you the mean photocurrent. Divide this one by the total noise variance, right. So, you have 2q mean photocurrent, which is R P1 e power minus alpha L times B plus 2 kT by RL into B. So, you can probably put B as a common factor and then take it out and then you evaluate this one. So, this is what is going to be the Q factor. Okay. So, if you plot the BER as a function of the fiber length, okay. So, as a function of fiber length for different launch powers mean different values of Pn, right. This is the power that I am launching. So, this is called as launch power, and in this case launch power is the power that is carried by the bit 1. Okay. So, if you look at fiber length in kilometer versus BER for let us say about 10 to the power for 0 dBm, the BER more or less is about 10 to the power minus 5. Okay. This is not, this actually depends on the system. I am just giving you some values which kind of make sense for a typical 10 Gbps systems. Okay. So, with a 10 Gbps system with an electrical bandwidth of 7.5 gigahertz and RL of 1 kilo ohm with a responsivity assumed to be 1 ampere per watt, this is what the BER is. Of course, fiber loss is 0.2 dB per kilometer. Now, this is not even meeting our specifications, right. So, this is not even meeting our specifications, and this is not something that you would like to use for. If you want to use this system, then what you would like to do would be to increase the launch power. So, if you increase the launch power, then the BER starts to go down. Okay. With this 0 dBm launch power, the BER is not even going below 10 to the power minus 5, but if you use say 2 dBm launch power, then you might be going below to 10 to the power minus 9. Okay. So, this is already sufficient. In case you increase your launch power further, then the BER goes down to 10 to the power minus 20 or 10 to the power minus 25. This would happen for a 4 dBm system, and all these values. So, if you look at this particular line which I have drawn, this is for 140 kilometer, according to the calculations for the system values that we did. So, you see that this value is actually increasing as you reduce the optical power. On the other hand, if you increase the optical power, the BER of the system starts to decrease. Now, this is all for a system without any amplification in the middle. Okay. Suppose I put an optical amplifier followed by a band pass filter, or rather I should put a band pass filter first and then follow it up by an amplifier. So, if I do this kind of a receiver before I give it to the photo detector, and hence for the further processing, these curves will undergo a drastic change. The curves will actually, for higher lengths they will all kind of converge, but at lower lengths of the fiber they would actually exhibit a behavior that goes like this. This of course depends on what is the gain of the amplifier that you are looking at and what is the bandwidth of the optical filter that you have, but the general idea is that with this amplifier at the input of the receiver side, this is called as the pre-amplifier. With the pre-amplifier you are able to meet, let us say this is the target 10 to the power minus 6, you are able to meet the 10 to the power minus 6 target right at a very large length. So, let us say this is around 200 kilometer. So, the use of an optical preamplifier is to extend the range over which you can communicate. So, from 140 kilometer you can go all the way up to 200 kilometer. Okay. So, this is all about the performance measure of the on-off keying systems, which is disturbed only by the loss. In the next module we are going to look at the performance measure when there is chromatic dispersion, right. So, before we go there, there are some worksheets that I will send out. So, please solve some of the exercises. You have to reproduce these graphs for the parameters that we send in. Thank you very much.